Okay, and now we transition into the panel discussion. If I could have all the speakers come up. We've had a lot of fun preparing for this. So the questions themselves were difficult, but this is what we settled on. We're going to go through person by person that will offer their input, maybe some commentary. I've told them to keep things clean. And then I'm going to throw it out to the audience. Please feel free to ask questions directly about what they've said, and if you have things that were brought up today that you didn't get a chance to ask. So the first question, we phrased it like this. How many progenitor channels are required to explain observations of supernova 1A? And we were trying to focus on those on the Phillips relation, but we may need to draw on other examples to explain that. From there, how many progenitor channels, which are the progenitor channels do they favor? And then looking to the future, what theory and observations are needed to help resolve these issues? You know, we're up to thousands of supernovae observed. How many more do we need to answer this question? And perhaps what theoretical motivations we need as well. All right, so I'm going to ask Saurabh to begin. Here's the master slide that we'll refer to. Okay, and there's the Phillips relation on the bottom. So, Saurabh, would you like me to move the first slide, or do you want to begin there?
Yeah, let's start with this.
Great.
So, so thanks to the organizers for having this panel discussion. It should be hopefully interesting. The question in the program said singles, doubles, or triples, and so that's one aspect of what the progenitor question is. But I tried to list a thing of what we know about these, and we heard a lot about this morning. And I think the only thing we know for sure, pretty sure, is that these 1As are explosions of CO white dwarfs, and the question of its single, double, or more progenitors, it's a bigger question. I mean, the things that we don't know, do they explode at the Chandrasekhar mass? What is the companion? That's one aspect of it. How does the explosion proceed? We heard from Wolfgang all these different ways that the explosion could actually go. Interaction with what stuff, and we heard that stars are just dense versions of circumstellar medium. And what's left behind? We also heard from Wolfgang that sometimes these explosions are not completely successful in disrupting the white dwarf, so there may be remnants. That's not something we've talked too much about in the field. And then, many people, Ryan, Wolfgang, have suggested that there are multiple, answers to these questions. And so the question there is, what is the mixture of these? How many of these different kinds produce the results that we've seen? I had a newer version of this slide, which had one other question.
I'm sorry.
Which is, why do we care? And what do we care about? So, there's some people who work in this field who only use these 1As as cosmological tools. And so the answers to these questions some of these questions may be important for using them as cosmological tools, but maybe some of them are not important. I think for most of us, maybe I'll try and speak for everyone, is, we're also interested in what these objects are. We've heard they, produce half the iron in the universe. They're, really important astrophysical objects, so we would like to know the answers for that reason. So on the bottom, just for the people who, we may start talking about some weirdos, and I'll start. So I just wanted to show a Phillips relationship where you can see that the bulk of the supernovae follow this very tight relationship. So whatever the answers are to these questions, most supernovae, most white dwarf thermonuclear supernovae are on this Phillips relation. There's some extremes and outliers, and there's this cloud of oddballs called 1AX, which maybe I'll start with that. On the next slide. So in the question of single versus double degenerate, what we do for core collapse supernovae to look at progenitors, we like to see pre-explosion detections of these things. So from 87A, there's a whole laundry list of core collapse supernovae type 2Ps where we have a pre-explosion detection, and that tells us something about it. So there's only one white dwarf supernova or one thermonuclear supernova where we have a progenitor detection, and it's not a normal 1A. So one of the take-home points for me is that when you think about white dwarf supernovae, yes, most of them are normal 1As, but some are not. And the only one is this one that Ryan mentioned at the beginning of his talk, supernova 2012Z, where we see a luminous object, absolute magnitude -5, at the position of the supernova taken before the explosion. And so our interpretation of this, and I can go into the details of why all these words are there, is that this is a pure deflagration of a CO white dwarf that was probably the Chandrasekhar mass, that was accreting from a helium star. So what we think we are seeing is the actual helium star companion that was the donor to the white dwarf that exploded, and that this model leaves behind a bound remnant. So there are arguments from this class of weird 1AXs for all of those things. And the real question then is what's different about normal 1As? Is it that word deflagration? So do you have to have a detonation for a normal 1A? Most people would say yes. Chandrasekhar Mass, we heard from Wolfgang that his favorite models now are sub-Chandra for the white dwarf mass, so that's very interesting. Accreting from a helium star, what is the accretion? That could be different. And leaving behind a bound remnant. So we would expect probably for most normal 1As that there shouldn't be anything left behind. So maybe every single one of those words is different from a normal 1A. And to me, the question is, what is the physics that's controlling that? So the last thing I wanted to say is that in September at this year, we're having a conference in Garching. Stan and Mariam and I are coordinating. Actually, Kate McGuire is really leading the organizing of that, and Klaus Franzen. So it's actually a month-long workshop, but the last week there's a topical conference on Supernovae, the outlier. So if you're interested in weirdos, you can come to Munich. Actually, the last day of the conference is actually the day before the beginning of Oktoberfest, so another reason to come. So hopefully weirdos are telling us something interesting about normal objects.
Okay, great. We'll just go in the order of the slides. I believe Yi.
All right, let's come to another weirdo. This is also a low velocity one, which is similar to type 1A X supernova. And in the morning, we heard from Bob about this supernova interaction signature that we expect to see from the single degenerate channel. And we found like 12 CG, which might show this supernova companion interaction signature. But in this window, which we call 1480G, we do see a strong declining UV emission at a very early time, which is shown in the red light curve here. And in comparison, I'm showing you in gray the supernova, type 1A supernova UV light curves from Swift before the IPTF era. And in purple, I show a lot of upper limits that we did for normal type 1 and the weirdos in the IPTF era. But 1480G is the 1 out of the 10 supernovae that we triggered Swift observations that actually shows a strong UV declining emission. And we used Dan Kaysen's model to interpret this early UV light curve, and we find that this is actually consistent with the binary separation of about 70 to 90 solar radii, and assuming zero Schlop filling. And so this kind of weirdos, people may think it's a pure deflagration of the of a white dwarf, and actually we also find evidence for that. Next slide, please. And from the spectrum of this supernova at around max, before max and near max, we see strong carbon-2 absorptions in the spectrum, and in the nebula spectrum, we also see these unusual oxygen-1 nebula emissions, which all indicate unburned material at both high and low velocity ejectors. And it's quite consistent with pure deflagration of a white dwarf. So if we put things together, this supernova is an explosion of pure deflagration in a single degenerate channel. So this is one example. It's a weirdo, but we think this might this is indicative about the detectability of supernova companion interaction in this UV, and we should definitely apply this to a large sample of normal type 1 supernova to actually see if there's any supernova companion interaction signature. And I hope to find a more solid evidence than 12 CG that Bob mentioned in the morning.
No, I think, Armin, your slide's next. Sorry. Yeah.
So I think there is a conflicting evidence there's evidence for several channels to produce a type 1A supernovae, and I want to just mention a couple of them that I have worked on. So one is we have light curves of type 1A supernovae with a Kepler telescope, which has, of course, an excellent cadence every 30 minutes. And where is it? Well, I mean, you can see it here on the left. They are just like absolutely beautiful light curves. Okay, here we are. And so these are all most likely normal type 1A supernovae. We don't have spectra, unfortunately, for this set. And as you can see, there's absolutely no hint of any interaction between the supernova explosion itself and some massive star AGB star, giant star, or even main sequence star, you would see some kind of effect in the early light curve, and we don't see anything like that in contrast to what Yi has found. So we also have now more light curves from the Kepler-2 missions of Type 1a supernovae. I think probably another 7 or 8 Type 1a supernovae, and just a preliminary analysis does not show anything that pokes into your eyes. I mean, the Kepler-2 data are not as high quality as the Kepler-1 data because of the the technical issues that there are now. So we do still have to work a little bit on the light curves, but there's nothing that we think that really jumps out at you. So from the Kepler light curves, it really looks like that there is not much signatures that can be seen. There are two explanations for that: either that it's double degenerate or some other channel that does not involve any normal star as binary companion, or that's interaction between the supernova and this companion star does not give a really strong signatures. I have to say we are in the red band, so the Kepler passband is R and I, and of course any interaction with the binary companion you would see much more strongly in the bluer bands. So, unfortunately we cannot pick the filters that we're using. That's just like what we have to live with. And then another aspect is if you actually look into the local universe in our Milky Way, you can look at the supernova remnants. And from the 7 supernova remnants that are relatively young in our galaxy and the 3 in the LMC, 3 out of these 7 supernova show signs of interaction with the circumstellar material. That's a Kepler N103b and RCW86. And that's kind of like an indication that there should be some, that is a single degenerate channel that produced these supernovae. So I think it's actually really confusing because there is the strong evidence that we should find at least some Type 1As with from the single degenerate channel, but we have not found any direct evidence yet that it's really common besides Yi's work and also Howie Marion's work, where they found with Swift data in the UV some excess. So I think overall it's just still very confusing. I think more than one channel has to be responsible for Type 1As. My gut feeling would be that it's more double degenerate and less single degenerate, but I think that's still to be determined.
Okay, Doron?
Thank you. Can you please go back to the Phillips 2005? So before, I just want to say something about the title of this discussion. That is single, doubles, or triples. So I think it's a very confusing title because let's say single is 1 white dwarf, double degenerate is 2 white dwarf, but triple is not 3 white dwarfs, right? It's also 2 white dwarf. And in fact, what we know now is almost all tight binaries are in triple system anyway. So in fact, probably all these systems are in triple systems. So what we really mean is something else. What we really mean is why these white dwarfs explode. So for the single degenerate, what we mean is some slow accretion build up to the Chandrasekhar limit that somehow explode the star. With double degenerate, we mean some fast accretion to reach to the Chandrasekhar limit. In collision, it's collision. So this is, it's like 3 completely different things: slow accretion, fast accretion, and collision. And this has consequences, of course. But before I go there, I want to say something about this Phillips relation and about single progenitor or multi-progenitor for this for the 1As. So I think it's quite amazing that this is so tight. And I don't know if you noticed this, but in Wolfgang talk, there was a little gap between the guys here and this 1PG. So I think this is very misleading because as far as we know, there is no gap. It's all completely continuous line. And 1AX, there is a gap. So mostly they are something different. So I don't want to argue about them because I don't know, but I want just to consider them the 1A. I think all of them, from the 91 BG to the Super Chandra one or whatever, all of them are just sitting with 10% scatter. So something is going on there. This is not by chance. Something is going on there. And I realize that many of the people in the audience don't used to see delta M15 at the B-band and stuff like this. So let me refer you, let's do some analogy to something else. Let's do the Hertzsprung-Russell diagram, where we see zero-age main sequence stars. And there is some continuous line, right? I don't think that anybody says, okay, let's first try to understand the G stars and then think, oh, maybe it's the same channel as the A stars, right? It's obvious they are all the same thing. And we don't say, okay, maybe there are multi-channels for powering stars. Maybe F star is something and the A star is something else, right? Nobody even thinks that. You know what was the last guy that thought there are two different mechanisms for powering stars? No one, because this is the point. This is just the point. It's a continuous line. So, okay, so let's go on. I want to show you that this is really something which is astonishing, this scatter. So if you can go to my plots. So this is actually Woosley and Kazan from 2007. So the line here is not really the Phillips relation. It's looking a little bit different, but the scatter is correct. And what you see here, this is a very simple game that anybody can do. You keep constant mass, okay? And you just change the nickel mass, the intermediate elements mass, but you keep everything else constant. And you see that you can get like a huge range, orders of magnitude. But the scatter is 10%. So what's going on? Even stuff that we expect to change, like for example, the carbon-oxygen ratio, which we know must change because of metallicity, still. Okay, what's going on here? So I think this is a very strong indication that at least for the guys on the Phillips relation, there is a single channel. And any model that cannot explain everything is in a very serious conflict with the data. Okay, so now I'll tell you what is my favorite channel, I guess you know. It's collisions, and I think the advantage of collision, okay, so first of all, in slow accretion and fast accretion, we don't know that the stars actually explode. So it was not demonstrated. The ignition is always put by hand. For these guys, collision, it is resolved. We know. White dwarf that collide will ignite a detonation wave, and so this is a calculation for first principles. It's the only model that can do it. And this is why I say it's simple and robust. There is no turbulence, there is no deflagration, nothing. The physics is completely known. And we solved the ignition problem. Now, here is the two defining properties of 1As. A huge range of nickel mass, factor of 10, a tiny span in the Phillips relation, or if you want, in the gamma ray opacity, which is even easier to measure. How can you do such a thing? I think the only way to do it is to change the mass. You must change the ejector mass with the nickel mass, otherwise you just cannot keep these two things together. And by the way, if you look on Phillips 91, when he first discovered, he didn't say, oh, this is so good for cosmology. He said, oh, look, the mass is changing because I see this huge range. And you just play with the masses of white dwarfs that we see in the galaxy. There is no problem with the progenitors. You get the nickel mass range. You get the constant gamma ray opacity. So I think, for me, this is very, very strong because there are no free parameters here, and you get what you need. There's also a very unique prediction, double peak in the nebula spectra, which I won't describe now, but I do want to mention that now we are in a project that collects order of 100 nebula spectra and a volume-limited sample, and there is a clear prediction of collision to the amount of double peak nebula spectra that you need to find, and I do hope we find it, but we'll see.
Very good. Before I open it to the floor, is there anybody on the panel that wants to directly comment on collisions?
I just want to make one very quick comment.
That's why we sat you one away. That's right.
I think we all agree that it's a CO white dwarf that explodes. And the fact that you have different mechanisms to make it explode can explain that they still fall on the Phillips relation. I mean, you gave this main sequence stars as an example. We have red giants and we have M dwarfs. If you make a color plot, they land pretty much at the same relation, even though they are very different beasts. But they have the same surface temperature. That's the reason they have the same color plot. So I think your argumentation that, multi-channel can never produce a Phillips relation like that, I think it's flawed because we do have the same object that explodes. And how we trigger it and the details come from the different channels. But so that's the reason they can still have a relatively tight relation.
Anybody else? No? I'm open up to the floor. I see a big hand by Wolfgang.
Since Doron mentioned mine, so here are completely different scales. If you would continue, there are by now lots of type 1As that are spectroscopically normal, that have a delta M15 of something like 2, and have a luminosity of minus 18.5. So in reality, if you would plot that as I did it, then there's a clear continuation of the normal ones along the Phillips relation, but the 91 BGs are a completely different group of supernovae. You cannot connect them directly to all the rest of the normal ones. They're spectroscopically different, and they are fainter by almost a magnitude than the ones that are on the Phillips relation at a delta M15 of something like 1.8 or 2. So they are clearly different beasts.
To make collisions happen, if you start off with a binary white dwarf and bring in a third star, you've probably got to do that inside a star cluster, either a globular cluster, an open cluster, someplace where dynamics brings the three stars together. I'm assuming that that's what you're assuming. Would that then not predict that you would see a much higher incidence statistically of such events inside star clusters, inside open clusters, globular clusters?
Yeah, so okay, one thing to realize about the 1A rate, that it's very, very high. If you just compare it to regular star formation, you need to explode roughly 1% of all white dwarfs. So anything that involves globular cluster is just irrelevant. Even if you explode all white dwarfs in globular cluster, you're still a tiny fraction of the 1A. So no, we're not speaking about globular clusters. We're speaking about field triples, which are very, very common. And the way I usually explain it, do you know how we check in astronomy things which are very, very common? They're very close by. So everything which is nearby is very common. So the nearest system to us, Centauri, Alpha Centauri, is a triple system. So there is no problem of making triples in the field. They are very abundant. And in fact, just to give a simple number to remember, so Danny Dalmau showed time delay distribution. I don't know if you can figure out from the rate, but roughly half of the 1A supernova happens before 500 megayear. Now, 500 megayear, to produce a white dwarf, you must have a star which is a B star. And we know almost all B stars are in triples. So there is no problems with producing the triples. The question is, can these triples survive? Can you be able not to collide before they are white dwarfs? So more, there are caveats. But just the mere fact that many stars are in triples, I think it is what it is.
Is Alpha Centauri the right kind of triple?
Alpha Centauri?
No.
Is it?
Is it kind of triple?
Oh, that will make a 1A? No. The masses are far too low. Yeah.
Even though it is a triple.
No, all I'm saying, triples are very common. Triples are very common.
But are triples like the one you want? Are they common?
So the triples that we want are very typical in the sense that the semi-major axis of the inner binary can span a huge range. So it's anything between, 1AU to 1,000U is fine.
Let me put it this way. Have you seen a double white dwarf with the hierarchical triple that would?
Oh, yeah. So observationally, they are, of course, super hard to find because the triple star will usually be some M dwarf or some other star with a huge luminosity contrast. So it's very easy to hide this system. It's very easy. Oh, yeah. So I don't know why Danny didn't mention this because he did the calculation. So he actually showed that collision will also have 1 over T. The reason is the same reason that he showed, that as long as the time to collision is the power law of the semi-major axis, and it is for collisions, then you will get the 1 over T. It's like natural consequences.
And the killer argument is polarization. And so we have calculated for models like yours, a continuum and line polarization, and they're all highly polarized. So we have a couple of % continuous polarization and even higher polarization in lines. And only very few supernovae show that, and the ones that show it are the faint ones, not the ones like what you would predict. So the normal type 1As are all unpolarized. They have essentially a little bit, sometimes in linear polarization, in line polarization, but nothing in continuum. And your models would all predict quite a bit of polarization. So they cannot be the bulk.
I just remind the audience there are other people here also. So yeah, I didn't show this, I didn't see this calculation that you did, but Dan Kaizen, I don't know if he's here. So anyway, he calculated polarization for a collision.
6% is a lot.
Well, I do have here his results. Okay, there's no point in arguing about numbers because I have his plot that he showed in Chicago. And his plot was completely consistent with the polarization that we know. I would be happy to continue this calculation and see more of this, but so far it looks good.
Okay, I'm gonna.
Yeah.
Sorry.
And this was Kaizen result.
All right,
so.
I'm gonna throw the towel in right now. Just hold on a second.
So,
yeah.
I have a question. Since there are two people on the panel that really haven't talked about much, maybe we should talk about weirdos. And so in particular, I think Saurabh made a very elegant point that for 1AX, we have a very compelling story for what's going on there, where we have 24 different observables and it's all explained by a single model. It might not be right, but I think that's compelling. And then Yi, for the O2ES, the one thing that I'm still struggling with is that they're associated with old environments. And so I'm curious, maybe Ken knows the answer to this, but how do you get a single degenerate channel where you would see interaction, Roche-Loeb overflow, I'm assuming, for something that has, say, a 10 billion year delay time?
I think the companion has a long lifetime in the giant, yes. And also if we include the rotation effects, the delay time in ignition also. Okay, so.
Well, stop me if this was discussed before, because I have to apologize. I only got in recently. But I just wanted to mention something about the single degenerate models, which is that there are many cases if spin plays a role. So if when you have an accreting white dwarf, it also is spun up, similar to the way a millisecond pulsar is spun up, then there is a wait time after the mass transfer may have ceased until you can have the explosion. So there are many, many different things that happen. There are so many pathways in the single degenerate, from giants to subgiants to main sequence stars. The end state could then be, if you have spin up and if you have a wait time until you spin down, the end state could be a white dwarf that was the donor, no longer giving mass. The end state could be a very low mass star of the type you see in a CV. So I think when we don't see interaction or when we don't see evidence for a donor, we should have that important caveat in our mind. Yes, this rules out the donor being a star that would have had that interaction, but we should always put the caveat that is modulo there not having been any significant angular momentum transfer. And maybe then, if we keep that in mind, we'll see a pattern in the places where we do see interactions with circumstellar material and cases where we don't.
I'm going to go back to the original question as we wrap up here. And this is kind of a gut feeling response in the sense of how many progenitor systems do you feel comfortable explaining the Phillips relationship, right? I understand everybody's position here. One, you can look at it as just purely coming into the field with fresh eyes. You see a relation like that with such little scatter, you would want to be, you'd be convinced that it was one progenitor channel that would produce such a thing. And yet, we've heard this morning all this overwhelming evidence of, none of these scenarios seem to fit every single one of our observational constraints from other avenues. So I guess we can ask the panel, and maybe as we wrap up, a show of hands. How do you feel comfortable that there are multiple progenitors that would give rise to that relationship?
Yeah, I think there's a lot of evidence that, different things have to happen in different cases. So I think Doron makes a good point that, that is a very tight scatter. So to me, what it points to is that there's some sort of bottleneck. Different systems, to make a 1A that looks like a 1A, they have to get squeezed into some configuration that is tight in some parameter. What that parameter is. To me, actually, the most likely thing is that, we may have been led astray by the Chandrasekhar mass for a long time. This idea that a detonation of a 1.4 solar mass object, a white dwarf, is just, it's too luminous, so that can't be it. And then we went down this path of deflagration to detonation transitions. It becomes very complicated. And I understand the historical reasons for why you naturally get ignition at close to the Chandrasekhar mass. But to me, this idea that how can it be a recent idea that someone had that if you take a 1 solar mass white dwarf and just detonate it, it looks like a 1A? So I think from an observer's point of view, that's a good model to test. Now, maybe it's very hard to ignite. You need a double detonation. Maybe you need some very complicated thing. But there are lots. There's this recent paper, Ford and McKecker, about the binary orbit exciting modes in a 1 solar mass white dwarf. Maybe I'm not a theorist, so I don't know if that's a viable model or not. But this idea of coming up with different ways to ignite a 1 solar mass white dwarf. So to me, those are maybe the multiple progenitor channels that somehow will cause a 1 solar mass or 1.1 or 0.9 solar mass white dwarf to detonate. So those are the multiple parts, and then the narrowing happens is that only in that small range of white dwarf masses do you get something that looks like a 1A. And it solves this problem. You have a lot more white dwarfs there. You have a lot more chances. So to me, what it points to is what happens in the other cases. What happens when you merge 2.3 solar mass white dwarfs? What does that look like when we go to the observational future, when we're going to be able to see a lot more objects, a lot fainter things with LSST? Let's have predictions for that full range. Maybe that full range on Stan's plot really is realized, but just not as a supernova as we'd recognize it, but as something else. So let's make those predictions for what else we could see.
I know you didn't get a chance to say much. Is there anything you want to chime in here?
Yeah, so I feel like, philosophically, I feel like universe is so large, so every single possible channel will work. And mathematically, we also see a lot of things that may start with very completely different initial conditions, but they end up with very similar phenomena. So with that being said, I do believe there are multiple channels for normal type 1A supernova. And the next question should be, what's the right way for us to actually determine the fraction of supernovae from different channels? And actually for that, I think there are 2 ways to move forward. One is to look at the very early part light curve where the supernova emission is actually sensitive, very possibly sensitive to the initial condition. And the other way is to really look at the ejected mass estimate. Like we find, Scarzo has multiple papers about estimation of ejected mass, and there are some supernova with ejected mass of 1.2 solar mass, 1.4 solar mass. There are also things with 2 solar mass. But so, do we believe the 2 solar mass supernova ejected mass estimation? If it is true, it is really from the double degenerate channel. So these are questions that should be answered and will be answered with a lot of data that's coming up in the next few years.
Right. Is there anything? Okay, we're drawing low on time here. We could continue this. I hope that, well, unfortunately, there's no resolution. I thought we would get to it, but we didn't. Maybe another couple minutes? No. But I hope the discussion is kind of spurred on some further discussion that will continue through the meeting. Thank you very much, and enjoy lunch.